Linear algebra true or false sections function as conceptual minefields. These questions are engineered to identify the gap between students who have memorized a formula and those who understand the underlying logic that makes it work. We're going to analyze 12 actual midterm questions to see exactly how these traps are constructed and how to dismantle them. Proving a statement true requires a rigorous general mathematical proof. However, you can prove a statement is false using a single, extremely simple counterexample, often involving zeros, ones, or basic identity matrices. This is a scan from an actual exam. We're starting with question 5 to see how core matrix properties behave under pressure. Part A claims that if a system has infinitely many solutions, the matrix must have a zero row. We can disprove this instantly. Consider a 1x2 matrix with the entries 1 and 2. Set that equal to 0. You have two variables and only one equation, which results in infinitely many solutions, yet the matrix contains no zero rows. The statement is false. Part B states the product of a matrix and its adjoint equals a scalar times the identity matrix. This is the formal definition of the adjoint formula. The scalar is the determinant of A, making this statement definitively true. Part C claims that if AC equals BC, then A must equal B. Matrices do not follow standard numerical cancellation rules. If we define matrix C as a zero matrix, any choices for A and B will result in a zero product. AC will equal BC even when A and B are completely different. False. Part D claims every matrix is row equivalent to a unique matrix in row echelon form. The trap is the omission of the word reduced. While the reduced row echelon form is unique, standard row echelon form can take several different valid shapes for the same matrix. False. Part E states that if A is invertible, A plus A transpose is also invertible. We can use a counterexample matrix with zeros on the main diagonal and 1 and -1 on the off diagonal. It's invertible because its determinant is non-zero. But when we add it to its transpose, everything cancels out into a zero matrix. Since a zero matrix is non-invertible, the statement is false. These examples show that matrices rarely follow standard algebraic intuition. Relying on basic algebra rules without checking these specific behaviors is a common way to lose points on these questions. We'll now shift to question 4, which focuses on determinants and spatial geometry. Part A gives us a 10 by 10 matrix with a determinant of 2, and asks if the determinant of A times A transpose equals 4. Because the determinant of a transpose equals the original determinant, the calculation is just 2 times 2. The statement is true. Part B asserts that a linear system with more unknowns than equations must have infinitely many solutions. This graph represents a system with 3 unknowns and 2 equations. Visualizing this as 2 3D planes, we can see that if the planes are parallel, they never intersect. The system is inconsistent and has 0 solutions. False. Part C claims the span of 2 vectors in 3D space is always a plane. However, if those 2 vectors lie exactly on top of each other, they are linearly dependent. Together, they only span a single line. False. Part D suggests the union of any 2 subspaces is also a subspace. Subspaces must be closed under addition. If we take one vector from the x-axis and another from the y-axis and add them together, the result is a point that falls outside of both original axes. This failure of the closure rule makes the statement false. Part E states that any set containing a zero vector is linearly dependent. If we multiply the zero vector by any non-zero scalar and all other vectors by 0, the sum remains 0. Because we found a non-zero weight that balances the equation, the set is linearly dependent. True. Vector space questions become more manageable when treated as geometry problems. Visualizing how lines and planes behave prevents the abstract logic from becoming overwhelming. Let's look at question 1 at the top of this next page to test a specific term, the trivial solution. It asks if a linear system with a trivial solution is homogeneous. A trivial solution exists when plugging 0 into the system works. If matrix A times a 0 vector equals vector B, then B must be 0. Since a system equaling 0 is the definition of a homogeneous system, this is true. In the middle of this page, the claim is that if 2 matrices are row equivalent, they share the same determinant. While row operations create row equivalent matrices, operations like multiplying a row by a scalar directly change the determinant's value. The statement is false. Memorizing strict definitions for terms like homogeneous and row equivalent allows you to skip the calculations and move directly to the correct answer. Now we just dismantled 12 complex exam problems by applying simple counterexamples like zeros, ones, and parallel lines. This approach allows you to bypass the long theoretical proofs that usually slow students down. When you encounter a complex statement on your exam, avoid the urge to start a lengthy theoretical proof immediately. Instead, challenge the statement by testing it against the simplest mathematical cases you can imagine. You now have 12 specific logical defenses to bring into your next midterm. Applying the simplest possible math is often the most effective way to expose a flawed statement and clear the path to a perfect score.